of Wi-Fi 6 and beyond. Wi-Fi 6 and 6E and Wi-Fi 7. I just threw this up there because people say Wi-Fi 6 all the time. And I brought this in to tie to that question about the Wi-Fi Alliance naming scheme. They could have named it Wi-Fi 5, and then when 6E came out, they could have called it 6. But they wanted to compete with 5G, and so they just named it one up the number and then had to add it's E. And anyway, the numbers are just marketing terms, but a lot of people use them. I think if you're in this industry, you should be able to switch back and forth between ACAX, Wi-Fi 5, Wi-Fi 6, and just be ambidextrous between them. So a little about me. I do Wi-Fi. I've been doing it for a long time. You can follow up and contact me with a little barcode there. So let's get started. This has been a long journey from like 1999 until now. It's been over 2 decades. The Wi-Fi Alliance next year will be having their 25th anniversary for having Wi-Fi. So we've been at this a long time. Along the way, the complexity of Wi-Fi has increased exponentially, and I'm going to have some data to show that as well. So it's an evolution, but the complexity is the part that I want to focus on today, that it's getting more and more difficult to stay on top of everything because there's so many pieces there going on. So just a quick grid view. I like seeing things in tables. If you're an exam question writer, you love tables because you can ask so many questions off of a single table. So if you're taking any of the CWNP exams, tables are a great place for the exam people to write questions from. So you might want to understand this. Anyway, I set this up, and if you look over on the left side where it says years, the column in red, it's the number of years in between the upgrades. So in between 802.11a and B, there is actually 0 years. They both came out in the same year. 2 different techniques, and when we could get into the details, and I'm not going to go back that far. I just want to show as we went to G took 4 years, and to N took 6 more years. So it was a long time from the beginning of Wi-Fi until we got to N, which was kind of a big watershed event. The Wi-Fi Alliance wanted to start their counting there, so they called that Wi-Fi 4. And then only 4 years until we got AC. 6 years until we got AX. But in the last 2 years, we've got both AX with Wi-Fi 6E and Wi-Fi 7 is now available, and they're coming a little faster. Wi-Fi 8 is already is queued up, and they have committee meetings and they're talking about it and they're working through issues. So this is not only going faster, but it's going more complex along the way. I added the Wi-Fi name against the IEEE name, but look at the MCS index number, and you can see the correct answer to the previous question. It's getting way more complex as we move further down the line. The amount of possible, just an MCS index, which is the combination of modulation, coding, channel width, the options are mind-boggling, as is the max speed. If you look down the kind of the light blue colored column, there is lots more speed. And the question is, how are we getting there? If you look over at the far yellow channel, you can see the amount of channels we have available to us. When we went from 3 to 9, that was a huge jump. And then when we got to up to 21, we had 80 megahertz wide to work with. That was a huge thing. So anyway, this table, and you can get a copy of this. In fact, I think Ms. Heather is going to send one out tomorrow. You can just follow up on the table and look at that. But the complexity is mind-boggling, literally, when you start thinking about the little pieces that are changing. And there's so many little pieces we should think about. So this is a thing I made up a couple years ago to help in troubleshooting. And I'll step forward and then I'll come back a second. So for each one of the little bubbles, there's a box on the left side. And then on the right side, there is a list of things that you might want to look at in that issue. So if we just go down the third run down, it says RF media. And the things that you can check in RF media are SNR, primary data rate, secondary data rate, RSSI, co-channel interference, adjacent channel interference, average MCS, jitter latency, consistency, blah, blah, blah. There's lots of things on that one issue. Well, I put all those into little bubbles to see how they all interacted. If you wanted to troubleshoot Wi-Fi, any one of these red things, which is the Wi-Fi portion, could be wrong. And any one of this individual bubbles could have any 10, 15, 20 issues you might want to look at. And then in addition, since if there's a Wi-Fi problem, if there's a network problem and you're on Wi-Fi, everyone calls it a Wi-Fi problem. But even if it's one of the blue or the green, the LAN or the WAN links, they're still going to call it a Wi-Fi issue. And you'll note right in the middle between the red and the blue is the access point. And that's the piece that connects the wireless world to the wired world. Anyway, just to re-emphasize you need to understand how this whole process works, how the client device has an end user who might have typed the wrong thing, and then the client device has to make a decision on which AP to join. And then per packet, and that's the kind of little red box around the top, per frame it's going to send, the transmitter has to choose between a contention process to pull a time for they could talk, what MCS they're going to use at any one point in time, the overhead that's going to take place. There's DFS equations going on, and that's per frame, per transmitter. And then the bottom part is how do I join an AP and all the issues that happen to do with that. So yes, Wi-Fi is complex, and when we go to troubleshoot it, we need to be able to have a format or a structure to look at it. We also have lots of frequencies. There's a ton of radio frequencies. The ones we have inside our Wi-Fi world are very specifically defined. The 2.4, 5 gig, and now 6 gig are defined depending on what your geography is. You may have slight differences in transmit power, or in 6 gig, you might have a huge difference. Instead of 1200 megahertz, you only have 500 to deal with. But we do have frequencies we can choose from, and they all have different characteristics for us to look at. If we look a little closer at those characteristics, upper right side of this, you can see the 2.4, and then it got way more with the 5 gig, and then even more with the orange orange 1200 megahertz worth of 6 gig. I also added on the same slide a little ruler, and you can see the size, the physical size of the wavelengths of 2.4 and 5 and 6 gig. So that wavelength matters. The physical size of the radio wave we're talking about has a aperture. The radio wave is a certain size. The antennas then, in order to tune an antenna to that frequency, also need to match that size. Normally we're about a quarter wave, because the way a waveform works, a quarter wave collects most of the data. Now, a half wave antenna or a full wave antenna would be better, but they would be huge in some of these cases. So note the size difference between a 2.4 aperture and a 5 gig aperture. 5 gig is the blue one. If you can see on the slide, there's also a little teeny little change of color around the edge of this. And that color change is the difference between the low end of the frequency and the high end of the frequency. So there is changes inside those as well. Note the 6 gig, because it's 1200 megahertz wide, has a bigger band of the difference. And then look at the teeny little dot on 60 gig. So each frequency has a physical size, and our antennas are a physical size. And one of the things I can bring up here, just to reinforce this point, people say things incorrectly all the time. Like for 20 years that I've been in Wi-Fi, people say something really stupid like, yeah, 5 gig doesn't go as far as 2.4, which is totally wrong. If you had an access point and you transmitted on 2.4 and 5 with the same transmit power, they would both hit the moon at the same time. They would both hit Jupiter at the same time. And if you wait long enough, they would both hit Alpha Centauri at the same time. They both go the same distance. The difference is because of this, what you see on the screen. The 5 gig antenna is tuned to a smaller aperture, so it receives less energy than the 2.4. So it's on the receive side that there's a differentiation. It's not that that somehow the 5 gig waves don't go as far. It's the receiver just doesn't hear as well. Now, here's 2.4. And I don't know if you want all these details, but I put them on here anyway, just so you have a resource. We use the top for Wi-Fi, the green, blue, and yellow channels is what we normally use. But in addition, there's a bunch of channels that have a high amount of overlap, thus the screen, so you can see how much overlap. But our other friends who are using 2.4 gig, either Zigbee or Bluetooth or BLE, they break up that same channel a different way. And if you look down on the BLE column, there's a couple little yellow boxes that poke up a little bit. And if you're ever looking at a spectrum analyzer, you will see these little poke up little bits. Those are the BLE channels that they talk on a lot. And so that's why you'll see those. They tried to aim them between the Wi-Fi channels, one to the left, one between 1 and 6, and then the other one's far on the other side of channel 11. Now, 5 gig also has tons of details, lots of information depending on what your geo is, whether or not you have Doppler radar turned on or turned off. And there's a bunch of good stories about how we lost it in the United States because of one vendor. And then after years, we finally got it back. And so these are the channels we can use. Oh, I need to update this because over on the far right side is the Uni 4. And depending on what your geo is, you have access to a couple more channels over there as we squeeze over. Then we get to 6. Here is 6 gig using low power and standard power. And you note on the standard power in the bottom row, the black little parts, that's because standard power can't even touch those other channels. So if you go to a wider channel in standard power, you have very few channels to choose from as the wider you go because you're blocked off. Anyway, this isn't about all the channels. I'm just talking about the complexity as we see the different things as they move forward. One other type of complexity, we started out with, I didn't even put on the slide, BPSK. And BPSK is the simplest form of modulation we can use. You either send a 1 or a 0. So for every symbol you send on the radio, you get 1 bit on the other side. It's very robust. It works really well. For Wi-Fi that we're using now on Wi-Fi 4 and above, BPSK our minimum data rate is like 6 meg, which, by the way, I get a little frustrated sometimes when people go, oh yeah, it's so slow. Yeah, it's fast enough to send HD Netflix. So even the worst Wi-Fi with the most robust modulation still can take care of Netflix. So when people complain about Wi-Fi being slow, I think they're looking at different things along the way. But today we have 1024 QAM and even 4096 QAM, which means for every bit that we send out, the amount of precision that you have to have is mind-boggling. If you just think of if you look on the screen, the 64 QAM, there's 16 little pieces there, little dots. Sorry, there's 64. Duh, I said, my mistake. 64 QAM has 64 little dots. But if you look from the center out at an angle, there's 4 in a row that have the same angle, 45 degrees. And then there's different amplitudes along that line. From the center, if you looked at each and individual dot, you could see there's a slight change in rotation and then a change also in amplitude. Those are the two things. Quadrature, what's the angle, and amplitude is how far it goes out. And as we add more into these QAM symbols, the precision of both the listener and the sender have to get super, super precise. Now, we're not the first to use these. You've had it on your cable TV. Coax has been using 2K QAM and 4K QAM for a long time. But they have a bounded media. They're a lot tighter and able to control the noise and interference. In our case, with Wi-Fi, in order to maintain these super high QAMs, we have to have super high SNR, which means we have to talk really loud and not have a lot of noise, which also means we can't have co-channel interference along the way. So yes, we're getting speed and faster and more complexity, but it also means you have to be very close and or add more APs closer. So back to MCS. I've talked about MCS on this channel before. I know other sessions on 7 Signal have also focused on MCS. So you already know this. You probably have this one memorized. This was just the beginning of N and AC. The N was yellow and the AC was blue. But as we got more, when we got to AC, we picked up a whole lot more possibilities, which is great. Because if I have a client and he's talking to an AP and he goes to transmit and it didn't work, as in I send a frame and it didn't get an ACK, then that means I need to retransmit the frame. Well, these are the choices I can choose. I can change column. I can go from 20 megahertz to 40 megahertz. I can go from short guard interval to high guard, low guard interval. I can change my modulation, 64 QAM down to 16 QAM. There's lots of things that a client device can do to hone in on that sweet spot where they can get the most amount of traffic with also the most amount of acknowledgements. They want to make sure that every time they talk, the receiver receives it. Now, Wi-Fi is kind of backwards. We don't hear from the receiver. They don't respond and say, oh, I heard your thing, but it's a little off. The transmitter has all the responsibility. He sends it, and if he didn't get it back, he goes, I wonder what the cause was. Did I not send it because I was on too wide of a channel? So maybe the transmitter, because this works both AP to client and client to AP, the transmitter will make a new decision and say, maybe I should try something different, and these are the choices to choose from. A lot of choices means you could find a good sweet spot. But at one point in time, the choices get a little overwhelming. This is the AX choice. You can get this at mcsindex.com. It's run by Francois Vergès, and Francois just at WPC last week showed his new version for BE, for Wi-Fi 7. It puts this one to shame. It's way, way bigger, especially if you put in that there's option to go to 16 by 16, which is just crazy talk. So now we're getting to a level of complexity that even if I had choices, how is a client device going to make the decisions between these little teeny little things along the way? So back to these upgrade cycles. Let's look at that MCS column again. 2, 11, 4, 11, 77, 624, 1728, and now we're at 4032. That's a lot of decisions that some little CPU that's inside of a SoC, a little system on a chip, has to decide between those frame by frame as it's going. And as troubleshooters, we're trying to troubleshoot Wi-Fi, we have to deal with that same type of complexity and say, well, why did it make that choice from one to the other? The only slight little differences. Okay, so I instead of just looking at a table, I put it into a chart, which is not really eye candy because it's not very pretty. But what it goes to show is it's way, way more complex. And we're stuck having to live through this. Now, back up, I did a separate one, and you can probably go to what Heather said, out to the resources, either the YouTube page or to Seven Signals, what do you call it, Heather? Training site? Whatever.
Sorry, I had to find my mute button. It's the Wi-Fi University.
Wi-Fi University, sorry. Yep. So I did a whole previous 1 hour on this one slide. But if you look at it, to deliver one frame, and the payload is the blue, everything else is just overhead. Wi-Fi has a huge, huge amount of overhead. And even though we moved to 6 gig, we didn't get rid of this. It's still there. So even when you're saying, well, do I go to 40 megahertz channel or 80? If you note, the bottom one is the difference between the 40 and 80 megahertz channel. The amount of actual airtime doesn't change that much. Yes, you deliver twice as much or 4 times as much payload, but as a percentage of the actual airtime, it didn't change all that much. So this complexity is still there. And if you don't understand the red, green, orange, light yellow, green, as those step through there, spend some time, maybe go back and research this, because understanding how a single frame is transmitted helps you do all sorts of troubleshooting and making predictions for the future. So if you can believe marketing, these are the new things we're going to have. Wi-Fi 7 is going to be awesome. Yeah. We're still stuck with Wi-Fi 6 and talking about, is it possible to get BSS coloring to work? And I've talked to a bunch of vendors and they're all like, yeah, we don't even turn it on. But the marketing guys talked about it for years. How about OFDMA? Yes, we have wonderful OFDMA, but we're still in a point where they're hard to even capture the frames because they're not, and it's been around for years. So some of the things like MLO that's coming in Wi-Fi 7 may work, but it's still marketing. So instead of marketing, let's look at what's reality. How do we do real world testing? I give you an example. at WLPC Prague last week, Wes Purvis gave a presentation, and in it he talked about a very large IT organization doing a conference, and tens of thousands of people were there, and they had a penetration of 6 gig clients all the way up to 10%. Yeah, so and now that we have iPhone 15 Pros have 6 gig, I'm sure that's going to climb. And I'm sure in those of you who are in the edu world after Christmas, there'll be new devices coming on in January that will be more 6 gig capable. But we need to be doing testing and realizing all these new features that are all future proofing. One, are complex. Two, we're not going to see those benefits until the clients join as well. So a couple places you can go look. These are from last year. We haven't posted the WLPC ones up, but if you go to the YouTube channel for WLAN Pros, they should be up within about a week or so. We've got them all captured. We're just going to be posting them. And in Prague, there was a lot more sessions on Wi-Fi 7 that you can catch up on. So I want to sing along a little Sesame Street song. One of these things is not like the other. We live in a world where we have Wi-Fi and CBRS and Halo and LoRaWAN and carrier cellular. And sometimes people get confused between what frequencies they use and who pays for what. And there's a stark difference between those that are Wi-Fi, Wi-Fi Halo, Wi-Fi, LoRaWAN and Zigbee use some of the same channels, but entirely different protocols. CBRS and private LTE use a LTE protocol on their own private bands. And then carrier cellular is used on bands where someone leases or rents, or you pay per byte for that space. So CBRS, Wi-Fi and Halo are unlicensed. So is LoRaWAN. Private LTE is lightly licensed, but then when you get to the carrier cellular, the actual frequencies. So when people are talking about these different options for wireless connectivity, go back to that slide on frequencies. Not just what are the frequencies, but who pays for those frequencies. So do you need to upgrade today? I've had a lot of people ask, oh yeah, you should. I've been at hotels that still use 802.11g. And I can sit in my room and stream the Netflix show I want to watch. I can do all my email. It works. A well-designed Wi-Fi that's 802.11g still provides a certain level, and it depends on capacity and throughput requirements. But 54 meg data rate that you net out 20 is enough for all sorts of things. And we have a lot of channels that can deal with that. So if you're in 802.11n, even more. So when your customers say, well, should I upgrade? The answer isn't like yes, no, now. The answer is, what's your upgrade cycle look like? So we need to talk about a few things on the upgrade that we need to be caring about. As we move forward, we need to think not only about backward compatibility, what devices do you have, what are they using, but also forward compatibility, that as we look forward, that new devices will continue to work and not break as we come up with new things. The whole multi-user MIMO up and down still is yet to be proven by anyone. It's an idea and it's a technology that may work. We're still waiting on that one. Do you need multi-gig on your Ethernet? This has been a question people have had for a long, long time. Today, maybe not. But if you're going to upgrade your switch anyway, and you do need to upgrade your switch because of the next line down about AF power isn't enough, we need more PoE power. If we need more PoE power anyway, you're upgrading your switches, well, why not go to multi-gig? Today, we can get, if we push really hard, we can make one AP with a 2.4 client and a 5 gig client and a 6 gig client push and actually need more than a 1 gig Ethernet can do. It's kind of contrived, but as we move forward with tri-band radios and even more data coming in, you should think about moving to multi-gig. We now have Wi-Fi security issues, and if you want, there's a lot of talk about the difference between WPA2, WPA3, and when you need both. And we had bunches of sessions that we had on those specific topics in Prague. And if you're a supporter of EduRoam, yeah, EduRoam is only one SSID, and how are you going to deal with that one SSID in those multiple places? Now, the final slide and the bonus here is, we can talk about infrastructure all we want, but what we really need to be talking about, it's all about the clients. When the clients have the features that we need, then the infrastructure will support it. Now, you don't want your infrastructure to be behind the clients, because clients move a little faster. And this whole topic today was just to get you to start thinking about, where are you today? What are the things that are working today? And as you move forward, look at your clients. Where's your client base? What are they doing? And the whole goal is, of our Wi-Fi is to make sure the clients do what they need to be done. So Q&A time. Anything queued up? I was presenting, I just noticed somebody raised his hand, so.
Yes. So just so attendees know, if you do have any questions, throw them in the Q&A panel. We don't typically like spotlight during these sessions, but if you put it in the Q&A panel, we will definitely get to it. Forrest, as usual, has several riveting questions for us.
Okay.
So let's start from the top for him. So Forrest is asking, and I'm sorry, this is kind of the first time I'm really taking a peek at these, so if I mispronounce things, you may shame me. Are the 6 320 megahertz channels valid in the US now? Channels, he's talking about channels 3195, 159, and 63.
In the US, yes, and there are Wi-Fi 7 shipping. I don't know if all of them are. As long as they're low powered, they should be in there now. So as long as they're low powered devices, those are still valid. Yeah.
Perfect. And then for a second question, is 20 megahertz channels is the 20 megahertz channel 233 an actual usable channel?
I don't know. I have to go look at that. I've never had that question before, but I will track that down, and if you send me Forrest's email, I will follow up with that.
Perfect. All right. And then third question here, why are channels designated as being in UNI 5, 6, 7, 7, 8, and 8? For example, are there specific equipment models that only work on UNI 7, 8? Or who, I think that's supposed to be, designated. Who designated those frequencies being in a particular UNI bands?
So that's a US FCC ruling, and they have all sorts of weird naming conventions. Both FCC, FAA, legal documents break them into those bands. Those bands existed for a long time before Wi-Fi came along. And so when we pick a band, it just happens to be, pick a frequency, it's already in a predefined band. So those bands have been around for a while. And then someone else asked about MU-MIMO worth the overhead. Specifically in a classroom or no classroom, I still haven't seen any vendor outside of a lab environment show that MU-MIMO works in a real world environment. Most clients can't support it, and it's as Devin Aiken says, it's a if, who cares? There's so many things that have to take place in order for it to work. But that said, MU-MIMO is leading, and the practice and the learning that the chip developers had on that are leading us to some things that we can have in Wi-Fi 7 that have potential to make things better. They might not be working right out of the gate as well, but a lot of these things are just practice. And we had OFDM like in 802.11a, and we've been working with it for a long time and getting it more and more efficient. So yes, we have to try the things. The chip manufacturers make a new piece, a new technology, a new idea academically. They turn it into silicon, then they test it, and then the vendors try it. And eventually we have tools that we work and love. So today, right now, I wouldn't recommend it. I don't think you're going to see any benefit. But if we don't push the limits, boundaries sometime, it'll make it difficult to move forward. So.
And this is a good one. Just asking for some recommended resources. You are a treasure trove for resources, and specifically asking for Wi-Fi networking beginners. This is from Anonymous. So what do you got?
Wi-Fi University, of course. You have hundreds of places to go. My company, Wireless LAN Professionals, has a YouTube channel with hundreds of videos that we've taken, both training videos as well as all of the WLPC presentations. So if you have the time, and you like learning on video, there's a way to go there. I still think CWNP, first one up, the CWNA, especially the book by Coleman and Westcott, is still the reference guide. People still use it. I leave it on my shelf. I check it out all the time. It's on my iPad for me to go do resources too. So the Cybex book, CWNA Study Guide, is one of the best places I go. If you want to get in deeper into the protocol, there's places you can go to the protocol. You can go get the protocol itself for free from IEEE. I don't think you'll learn very well that way, but some have. Yeah, there's lots of learning. Someone asked about BSS coloring. It should work better. What it does is it says, if we put this little color on our specific SSID, then others should ignore it, so we can have co-channel interference and yet punch through the interference and ignore things that aren't my color. The problem is, in the real world, it doesn't work. Sometimes I've had someone give a presentation where after lots and lots of work in a lab environment, they got 5% improvement. That's a lot of work just to get a little teeny benefit. So yeah, BSS coloring is just one of those things that was a good idea. But is there a reason the MCS is given preference over RSSI and SNR? And it all depends on the people coding the actual decision tree inside of the transmitter. So the transmitter says, I just heard some client device at a certain RSSI. I mean, some receiver I want to talk to at a certain RSSI. I can then compare that to my SNR and realize both RSSI and the SNR, the N in SNR, the noise, are both kind of made up numbers. They're not real. If there's data, we pull them off of data frames and Wi-Fi frames, but there could be really bad raw RF and we wouldn't pick it up with those two tools. That's just how they work. So those two numbers are useful to make a guess. The transmitter device hears RSSI and SNR and says, based on that, I'm going to try this MCS, which is a combination of modulation, coding scheme, channel width, and guard interval. At that point in time, the MCS is going to be how we transmit. After we transmit, if we don't receive an ACK, we don't know why. What's the reason that my frame that I can put together in that certain combination, the receiver didn't send me back an acknowledgement? Now, one of the things the transmitters do very fast is go, well, that didn't work, let me try it again. Because they're assuming there might have been contention. And in the random back-off timer that we deal with, I just might not have, someone else might have hit at the same time. And so the first thing we do is I'm going to try the same thing I did last time. I'll try it again and again and again. And depending on the coding that's in the actual chipset, it might try 4 or 5 times and then say, well, that didn't work. What should I try now? Now, what the transmitter doesn't know is why it didn't work. Did it not work because I transmit on a wide channel, which gave me a certain SNR? And if I go to a narrower channel, I'll pick up 3 dB more in SNR. So maybe I should just change from a 40 megahertz to a 20 and try again. And so some clients will make that move. They'll go column to column. It could have been caused by a guard interval mismatch. If the receiver that I'm transmitting to is far away and I have the wrong guard interval, they might not have been able to put it back together because there was contention in that little guard interval space. It could have been that I used the wrong coding scheme. I didn't have enough forward error correction, so I might want to add some more forward error correction and try it again, but everything's the same, I just changed the forward error correction. Or it could be that the environment is so noisy that I need to change my actual modulation. Any one of those could have been the reason. And so the reason we stick with the MCS as we're talking about it is because the RSSI and SNR could be the same, and different MCSs could react and work or not work with those two staying exactly stable. So we moved to the MCS because it's a more precise way of talking about things. I could be in a world where I have really low SNR, but I'm getting really good MCS because my communication from my transmitter to receiver, every time I send one at that MCS, the receiver acts me back, so it works. So that's more important than what the actual raw numbers are. PoE over multi-gig. The reason I brought that up is you need PoE today. The APs that we have, they need the higher PoE standard. You need BT, or they downgrade to be slower. So you just bought a brand new AP with 3 radios. It needs BT power. If you give it AT power from your switch, it will not perform as well as it should. It turns radios off. Depending on the vendor, they turn different things off. So the PoE is most important when you're talking about today's APs. The multi-gig, most APs today in most traffic and most places I've looked at don't exceed 1 gig threshold through their Ethernet port today. So that's why I say the PoE is more important than multi-gig. But if you're out buying a new switch anyway, I just upgraded my switches in my rack in my house, and I put in multi-gig because I wanted I needed the BT power, and BT power switches came with multi-gig. So yeah, they kind of go together. If you want to future-proof, and depending on your company's renewal policy, the issue with switch renewals is you might be on a 5-year or a 7-year for switches. They're on a different life cycle usually than Wi-Fi. So if you're going to be buying them and you're going to have to sit on for 7 years, you definitely are going to have multi-gig needs within the next 5 to 7 years. The Forrest asked another one about iOS. Oh no, sorry. Christian asked about iOS devices can't monitor and get the AP list when 6 gig only. That is just changed. Last week, I sat a class with Rasika on packet captures. It's a Rockstar Wireless course on packet captures. And we tested and proved that today's iOS, I think it's with iOS 17 and above, both an iPhone and an iPad can join a 6 gig only AP. 6 months ago, that wasn't true, but I just tested it last week and found that it was true. That's not what Apple recommends. That's not what I recommend. Using the RNR in a 5 gig channel to tell you to go up to 6 gig is a better alternative than 6 gig only, but they do work. 6 months ago, it didn't work. I tried it in my house, and I can roam anywhere in my house on 6 gig only with iOS devices today. But I turned that off because I like the 5 gig, 6 gig as using the RNR. And if you don't know what the RNR is, go study up on that.
So just because you can doesn't mean you should.
Yeah. Someone asked about continuous monitoring MCS and retries. I think if we had Eric Kamuli here, he would give a good answer on that. You can put on packet captures, but obviously 7 Signal can track that for you live.
All right. Anything else in the Q&A panel, Keith? There's one from Gary asking for a good list of supported clients that are Wi-Fi 6E and updating Wi-Fi 7 client.
For a long time, as an industry, we'd owed a lot to Mike Albano, who put up a website showing 5 gig clients and what channels they supported. And for a while, it was like the Bible. I don't think he maintains it as well. It doesn't have all the 6 gig and 6 gig E. If you're out there and you're watching and you want to host that, I'm sure we can send tons of data to you and packet captures. WLAN Pros capture a profile, and we could just send them to you to be some place to share that. I don't know of any place right now that has 6 and 6E client characteristics available. And soon we'll need 7. Mm-hmm. Oh, by the way, in Prague at the WPC, Ruckus debuted their Wi-Fi 7 enterprise AP, and a couple of people in the room had Wi-Fi 7 clients and associated. So I have seen cool. Wi-Fi 7 in the wild actually working.
That I'm sure that's going to be a question forever. So thank you for letting me know that so I can just tell them. It can be done. All right.
Sachin, I think is the name. MCS table shows data rates and how does it impacts with no number of clients per AP. So clients per AP are nothing more than using up time slices. So I could have a really good MCS. My connection to my AP is great. good SNR, good RSSI, I can send MCS rates really high. If someone else on my same AP or a neighboring AP with shared the same frequency sends a lot of data, what will happen is that will fill up the time slices that are available for me to transmit, which means sometimes I will go to transmit with the MCS I had that was working really well, and I have a collision because someone else is talking at the exact same time. Now, we shouldn't, because the way back-off timers work in Wi-Fi, but it happens when you get overloaded, especially in very high density environments. This happens. So then my client would say, I tried to transmit with a high MCS and it didn't work. So it will try it again a couple times, and then it will downgrade and try it again. And the problem is, when that downgrade happens, what happens is I use up more airtime, and then they use up more airtime, and then we all slow down together. And then the person who is downloading a big movie gets off, and I slowly speed back up again. So I've seen many times clients complain, oh yeah, Wi-Fi sucks right here. And you go there and it's fantastic. And they said, but it didn't. And you go back and look in the logs, and what happened is too many devices on that same channel. So it's not per AP, it's per channel. Too many devices that were in the same collision domain caused them all to slow down. And when they stopped being overcrowded, they went faster again. And so watching that MCS, and I've seen MCS just go bounce, 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 bounce. In my room, nothing's changed, it just bounces. It's just constantly trying to find the best possible combination. When you add an external thing coming in, like heavy traffic on the same channel, that tends to drop down quick. It drops down quick and comes back up slower. If you ever watch it and you graph it, the MCS during a high collision rate time will drop quickly, and then even when it's gone, it slowly works its way back up to the same speed.
And the questions just keep, let's take one more and then we'll end for today, but pick whichever one out of these. And then I'll include Keith's email in the follow-up email for anyone who attended in case you want to reach out with additional questions.
Any difference in signal strength in terms of quality impact on applications? Variable between 45, 55, or stable at 60. I don't think it's signal strength as much as, so in my world, the evil that attacks Wi-Fi is, I'm going to call it co-channel interference. It's actually co-channel contention. The evil that happens is when people put in too many APs or too loud of APs, and too many devices can hear each other talk. The way the protocol works is, if I hear you talk, I will wait. That means I have a slower network connection. Even though I have great RSSI or a fantastic SNR, if I can't pull a time slice to talk, my application slows down. Now, we do have QoS that's built in the protocol, and people think, oh yeah, QoS will fix all sorts of things. Well, what it does is it statistically gives one group, like voice, a smaller queue to pull from. They still have random numbers, but they have a smaller group of random numbers, which means they pull ahead of non-voice devices. The problem with all QoS that fits in those categories is, now I have a smaller queue. If I have more voice that are also in the same queue with me, we're fighting over a smaller set of things. So our contention actually goes up when we go to a smaller contention queue. Sometimes you might have to take that voice and back it off to a video in order to give them a little more space to breathe, especially if you have a heavy environment where you have lots of voice clients. Kind of like if you think about Apple has this idea that their traffic should have a higher voice queue because they're better than everyone else. I'm not making any political statements there. I'm just saying that's how they use QoS. And so when you're in an environment with lots of Apples and they all put in a low number for their QoS, they bump into each other more than they should. And so it depends. Yeah, just to quote Sam Clements, it depends. I like to think about MCS as like a blood pressure, or when you go to the doctor, they check your blood pressure, they check your temperature. MCS and RSI and SNR are just metrics we look at. They kind of go up and down together. And I just find that MCS is a better self-reporting mechanism than the other two.